Welcome all of you in this online session. My name is Dr. Vishal Patil. I am working as an associate professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering, Hyderabad. The name of the subject is thermodynamics. In today's online session, we will study the fundamental things related with the applications of first law of thermodynamics, means applications related with the study flow processes. In previous lecture, we have studied the fundamental things related with the first law of thermodynamics, means for closed system, means for non-flow processes. The content for this presentation is: first one is study flow energy equation, next flow processes, next throttle process, means it is one of the application of study flow process, next application of study flow process just like nozzle, then turbine, next boiler, rotary compressor, reciprocating compressor, condenser and evaporator. The first point related with the today's online session is study flow energy equation. The mostly in engineering application, the situation occurs when the study flow conditions are achieved. The conditions to be satisfied are the following. First condition is the mass flow rate through the control volume is constant. Second one is the state of substance passing through the control volume at all locations remains constant. And third important thing is the transfer of heat and work from or to the control volume is constant. Thus, for the unit mass flow, the equation becomes in bracket U1 plus P1 V1 plus V1 square divided by 2 plus G into Z1 bracket complete plus Q is equals to in bracket U1 plus P2 V2 plus V2 square divided by 2 plus GZ2 bracket complete plus Ws. If mass flow rate is M, then equation becomes M into bracket U1 plus P1 V1 plus V1 square divided by 2 plus G into Z1 bracket complete plus Q1 to 2 is equals to M into bracket U1 plus P2 V2 plus V2 square divided by 2 plus GZ bracket complete plus Ws. Then this equation is called steady flow energy equation. If we are substituting the value of H is equals to mu U plus PV, it reduces to M into bracket H1 plus V1 square divided by 2 plus GZ1 bracket complete plus Q1 to 2 is equals to M into bracket H2 plus V2 square divided by 2 plus GZ bracket complete plus Ws. The next important point is flow processes. The steady flow energy equation for unit flow is given by H1 plus V1 square divided by 2 plus G into Z1 plus Q is equals to H2 plus V2 square divided by 2 plus GZ2 plus Ws. It can be also written in the form of dH plus d into bracket V2 square divided by 2 plus d into bracket Gz is equals to delta Q minus delta Ws. Then H is nothing but enthalpy. H is equals to U plus PV, means it is related to the internal energy of the system. Then dH is equals to du plus PdV plus VdP. Then du plus PdV plus VdP plus d v square divided by 2 plus dg into z is equals to delta Q minus delta Ws. According to first law of thermodynamics, for the moving system, to an observer moving with the fluid, the attention gets focused on the stationary system and therefore the equation is become du plus pdv is equals to delta q. Then This equation holds goods for the flow as well as non-flow processes. Then this equation reduced to VdP plus D into bracket V square divided by 2 plus D into Gz is equals to minus delta into Ws. Means delta Ws is equals to minus VdP minus D V square divided by 2 minus D Gz. Then Ws is equals to integration minus integration P1 to P2 VdP minus V2 square minus V1 square divided by 2 minus Z2 minus Z1 into G. If the kinetic energy and potential energy changes are negligible, then equation becomes Ws is equals to minus integration P1 to P2 VdP. The next process is throttle process. The process takes place in a such a way that the fluid expands from high pressure to the low pressure without doing any work, and there is no change in kinetic energy and potential energy of fluid. There is no heat transfer between this process. Such a process is called throttling process. As per the figure A shows the experimental setup proposed by Joule Thomson. Joule Thomson, it is a famous scientist. The experiment is properly known as Joule-Thomson porous plus experiment. As per this, the stream of gas at high pressure P1 flows in through one side of porous plug completely insulated from the surrounding and comes out the porous plug at lower pressure P2. Means as per this experiment, the equation becomes the energy going into the control volume minus energy going out of the control volume is equals to energy stored in the control volume, means remaining energy. But as per the steady flow equation, energy equation is based on the assumption that the state of fluid is the same at the point in the control volume, or the state of fluid at any point in the control volume is maintained the same. The mass going in is equal to mass going out. Thus, there cannot be any energy stored in the control volume. Means for this case, energy going in minus energy going out is equals to 0. Means m into bracket u1 plus p1 v1 plus v1 square divided by 2 plus gz1 bracket complete minus m into bracket u2 plus p2 v2 plus v2 square divided by 2 plus gz2 bracket complete is equals to 0. Means by this statement of process, the change in kinetic energy or potential energies are neglected. Therefore, u1 plus p1 v1 is equals to u2 plus p2 v2, where h1 is equals to h2. This process has very wide application in engineering practices. As per the figure B shows, the one typical example of throttling process when fluid passes in a pipeline through a partially open valve. The throttling is an irreversible process. Actually, throttling degrades the energy and dissipated in useful turbulence. The next important application of steady flow energy equation is nozzle. The nozzle is a contrivance to increase the kinetic energy of the flowing substance at the cost of pressure drop. As per this figure shows the nozzle, this section deals with the nozzle only. From the point of view, the application of steady flow energy equation, the equation becomes h1 plus v1 square divided by 2 plus g into z1 plus q is equals to h2 plus v2 square divided by 2 plus gz2 plus ws. The shaft work is obviously 0, then ws is equals to 0. The nozzles are thermally insulated and are characterized by high rate of flow of fluid. Then heat transfer is also negligible. Then Q is equals to 0. Then change in elevation between the entry and exit point is negligible. Then Z2 minus Z1 is equals to 0. Then this equation reduces to H1 plus V1 square divided by 2 is equals to H2 plus V2 square divided by 2. Means V2 square minus V1 square is equals to 2 into H1 minus H2. The next application of steady flow energy equation is turbine. The turbine is characterized by first important point is negligible heat transfer as it's thermally insulated and the flow rates are very high. Second one is negligible velocity change in the flow of fluid. Next one is negligible potential energy changes. It is a device for obtaining the work from the steady flow of fluid expanding from higher pressure to lower pressure. The expansion may also adiabatic due to the thermal insulation. Thus, the for the unit mass flow rate, the equation becomes for the turbine is V2 square minus V1 square divided by 2 is equals to 0. Then Z2 minus Z1 is equals to 0 and Q is equals to 0. Then the equation reduced to the H1 is equals to H2 plus Ws. Then Ws is nothing but H1 minus H2 for the turbine. The next application is boiler, which is widely used in day-to-day life. The main function of boiler is to generate the steam. The boiler is characterized by the following features. First one is the velocity change is not appreciable and may be neglected. Then V2 square minus V1 square is divided by 2 is equals to 0. Second, the elevation change between the inlet and exit point may be also neglected. Means Z2 minus Z1 is equals to 0. There is no shaft work. Then by selecting the control volume, it can be treated as a steady flow system and the main function of the boiler is transfer the heat to steady flow system. The steady flow energy equation reduces to U1 plus P1V1 plus Q is equals to U2 plus P2V2. Means Q is equals to into bracket U2 minus U1 plus in second bracket P2V2 minus P1V1 means Q is equals to H2 minus H1 for the boiler means rate of heat flow it is related with the enthalpy difference. The next important application is compressor. The main function of compressor is to compress the air. The compressor are divided into two categories. First one is rotary compressor and second one is reciprocating compressor. First one is rotary compressor. In this rotary compressor, the flow rates are very high and the processes can be treated as adiabatical. It can be treated turbine for the purpose of steady flow process. Here the shaft work is done and the fluid is compressed. Then Ws is equals to H1 minus H2 for the unit mass rate. Here H2 is higher than H1 and therefore Ws is negative or done on the system per unit mass rate. The next application of compressor is reciprocating type of compressor. It is a control volume includes the receiver which is of sufficient large capacity as not to allow any fluctuation of flow in discharge line. The reciprocating compressor may be treated as a steady flow machine, but due to low rate of flow and large area of contact with surrounding, beside a deliberate attempt to remove the heat to reduce the shaft work done on it. there is appreciable heat transfer involved during the process. Thus, the steady flow energy equation for unit mass reduces to Ws is equals to Q plus into bracket H1 minus H2, where Q is negative and H2 greater than H1. Therefore, Ws is negative or done on the system. The next important application of steady flow energy equation is condenser. The condensation, it is a reverse process of boiling, meaning condensation process, the conversion of vapor to liquid takes place. The condenser are mainly divided into two types for steam condenser, jet condenser and surface condenser. The primary function of condenser is to transfer the heat out from the steady flow system. In this case, there are two steady flow masses stream. It is characterized by first point, no shaft work, second one is no change in kinetic energy, third one is no change in potential energy. Means let mc is equals to mass flow rate of coolant flowing, then mv mass flow rate of vapor flowing, then h1c enthalpy of coolant at entry, h1v enthalpy of vapor at entry, next S2 enthalpy of coolant at exit, then S2V is enthalpy of vapor at exit. Then equation becomes Mc into H1C plus Mv into H1V is equals to Mc into H2C plus Mv into H2V. Means taking only one steady flow stream of vapor and condensing the heat rejection from the control volume, then equation becomes capital Q is equals to mv into bracket h1v minus h2v. The next application is evaporator, which is normally used in refrigeration process. The refrigeration is nothing but we are maintaining and controlling temperature below than room temperature is known as refrigeration. The evaporator is the most important part in the refrigeration process. The process occurring in the evaporator is the reverse of what happens in the condenser. Means it is a reverse process of condenser. In evaporator, liquid enters, receives heat at the constant pressure and leaves as a vapor. The shaft work means kinetic energy changes and the potential energy changes are negligible in this process. Then Q is equals to H2 minus H1, where H2 enthalpy of refrigerant at the exit and H1 is enthalpy of refrigerant at entry. The refrigerant is nothing but the heat carrying media during this process. In this online session, we have studied the fundamental things related with the applications of first law of thermodynamics, means for the steady flow processes. We have studied the basic fundamental points related with this point, just like steady flow energy equation, flow processes, applications of steady flow processes, just like throttle process, nozzle, turbine process, then boiler, then rotary compressor, reciprocating compressor, condenser, and evaporator. For more details, you can refer Refrigeration and Air Conditioning book by Professor P.R. Balani from Khanna publication. It is a good book for the reference. There are n number of applications of steady flow energy equations, but I have shortlisted the mostly wide used applications for this online session. In upcoming video lectures, we will study the fundamental things related with the second law of thermodynamics, their statements related with the Kelvin's Planck statement or Clausius statement, and their other things. This video is specially prepared for the under to clear the fundamental concepts of UG students. Then thank you very much for the patient listening. Thank you very much.